Hello, I welcome you all to this another interesting screencast, and it reads determine the normal force and shear force and moment at point C. But I'm going to add this, okay, and the shear force diagram and the bending moment diagram. Of course, this is not part of the problem, but I just thought of adding it. This problem is coming from the Engineering Mechanics Statics textbook, 13th edition by R.C. Hibbeler. We have a simply supported beam, and it is loaded with a point load at 1.5 meters from A and a rectangular distributed load from 3 meters to 6 meters both from A. So from 3 meters from A to 6 meters from A, we have a rectangular distributed load. Right, to start with, quickly let's draw the free body diagram. At A, which is a hinge, you expect two reaction forces. We expect AY, and we also expect AX. Okay, and then at B we have a roller, and we expect BY. All right, for the rectangular distributed load, for us to find the support reactions, we need to convert this to an equivalent force, and since this is rectangular in nature, we expect this rectangular load to be acting at the mid-center of the length of the rectangular load. And this one is going to be equal to 1.5 on one end from the load and 1.5 to the other side. And then this load is going to be equal to the area under the loading diagram. And let's write this as FEQ, which is the force equivalent. Like we said, is equal to the area under the loading diagram. So this is equal to the length of the load, which is 3, times the height of this load, which is 9. And this gives us a 27 what units? Kilonewtons. Great. So we have everything. Let's apply the equations of equilibrium. So let's start with applying the summation of moments about point A. So say summation of moments about point A equal to 0 anti-clockwise being our reference. Alright, what do we have? We have a minus moment being caused by 12 kilonewtons, so 12 by 1.5. And then what else do we have? We have another minus moment from the equivalent force, which is a 27 times what's the lever arm from A. This is 4.5, right? And then we have positive moment due to the reaction at B, which is By times 6 equal to 0. Great. Let me just move this a little bit. I think it's fine where it is. Therefore, our By is going to be equal to, grab your calculators, we'll have minus 12 by 1.5 minus 27 by 4.5, then divided by 6. So what do I get? I get a 23.25. Let me repeat my calculation. So minus 12 by 1.5 minus 27 by 4.5, then divided by 6. So we have a 23.25. Then summation of forces in the y direction equal to 0. What do we have? We have AY plus BY minus 12 minus 27 equal to 0. Since we already calculated what By is, we just replace it directly there. Okay. And once we replace it, then we'll have the value of Ay, which is equal to, this is going to be equal to 23.25 minus 12 minus 27. So this gives us a 15.75 kilonewtons, right? Let me just check it again. Okay, right. So 23.25 minus 12 minus 27 is 15.75. Okay. So this is okay. This is fine. So then we move on to the next step and find summation of forces in the x direction. What we have, of course, we just expect a zero in that direction because we don't have any force applied in that direction. So Ax is equal to 0. So we have all the reaction forces. What we need to do is to make a section quickly at C so that we find the normal force, shear force, and the moment. So let's do a shear. That is a green line there just showing a shear. So we have the left hand section and the right hand section. I'll go with the simplest one. Okay, which one do you think? Of course, you already know it as the left hand side. So let's pick the left hand side. It's much simpler. We have to go for simplicity. Great. So this point is B, and we have a By. Mind you, we already found what By is. Let me just indicate it there. By we said is a 23.25, and Ay is equal to, what is Ay? Is a 15.75. Great. So there we are. By we are saying is a 23.25, and then we have a distributed load where we've done the sectioning, so we need to replace that distributed load. And this one has magnitude of 9 kilonewtons per meter. But we will be interested in finding the equivalent force, right? So we have at this point here, we're calling C a shear force, VC. We have a moment, MC, and we have a normal force, NC. Okay, so our equivalent force and the length of this section is just a 1.5 meters. And the equivalent force, of course, this is rectangular in nature. We expect it to be acting just at half the length, which is half of 1.5 is a 0.75, right? And this load again is just going to be equal to the area under the loading diagram. So let's call this F, or F star equivalent. Okay, so this one is going to be equal to 1.5 times 1.5 times 9. Okay, so what does this one give us? 1.5 by 9. This gives us a 13.5 kilonewtons. Great. So we have found everything. Let's apply the equations of equilibrium. We'll start with summation of moments. So summation of moments about point C equal to 0. what do we have? Okay, we have a positive moment from 23, so 23.25 times the lever arm, which is 1.5. This one is causing anti-clockwise. Okay, about C. Okay, and then we have a clockwise moment from 13.5 times the lever arm, which is 0.75. And then finally we have a negative moment at C. So making MC subject to the formula, MC is going to be equal to 23.25 times 1.5 minus 13.5 times 0.75. Okay, so we have MC equal to a 24.75 kilonewton meters. Let me just check it. 23.25 by 1.5 minus 13.5 by 0.75. Great, 24.75. So we found that one. Let's find the other internal forces. So summation of forces in the y equal to 0. What do we have? We have a 23.25 minus 13.5 and then plus VC equal to 0. Therefore, our VC is just going to be equal to 23.25 minus 13.5. This gives us a minus 9.75 kilonewtons. Right, 23.25 minus 13.5, 9.75. Then finally, summation of forces in the x direction. What do we have? Of course, we don't have any force in that direction. Therefore, we expect this NC to just be equal to 0 kilonewtons. So we have found all what the question asked for, and these are the ones I'm outlining. But like I said, I was going to also draw the moment diagram as well as the shear diagram. Okay, so let's do that. So we know before we start drawing, I just remind you something that you already know. You know that the rate of change of moment with respect to x gives us the shear force, and from the same equation, moment is therefore the area under the shear force loading diagram, right? And we know also that the rate of change of shear with respect to x gives us the loading, which is the distributed loading, and therefore shear itself is the area under the loading diagram. With these two equations, we are going to draw the shear force and the bending moment diagram. Great. So let's start the work. Let me just draw the reference lines. So we have one there. Let's also put another one there, like so. Great. And then we have positive, negative, positive on top, negative down. Great. So I'll be using green. All right. So let's start. So we know that at A, we have this AY equal to 15.75. So we expect this movement, the shear here is going to go up like that. Let's imagine this is our 15. This point here is our 15. We can take note of it. So imagine this is our 15.75 kilonewtons. And then once we are there, when we look at this region here, let's name this point here as our D and then this one E. So when we look at the region between A and D, this region has no force, and by force I mean no distributed force. So our distributed force is equal to 0. And if that is the case, therefore we expect the slope of the shear diagram, okay, dv dx to be equal to what? 0. So that is just going to be a straight line from that region, from that part to D, okay? And the moment we reach at D, we have a force of 12. So you know what happens? Then those two are going to interact. So we'll have a 15.75 minus 12. What does this one give us? This one gives us a 3.75, right? It's a 3.75. So this shear will be reduced to this point here. Let's imagine that is our 3. So this point here is our 3. Let's write this one here is our 3.75 kilonewtons. Then between D and E, we again do not have any distributed loading. And this means the slope of the shear force diagram will be equal to what? 0. Okay. Just like in the first case. So we expect a straight line again from there to there, like so, up to E. Up to E. Okay, up to E. Okay. The moment we reach E, just before the loading there, okay. So this straight line just goes just before the loading starts, the 9 kilonewtons. Alright. So at that point, we have a different behavior. Our distributed load Q is equal to 9. Okay. Right. It's equal to 9. Our distributed load is equal to 9. Okay. And it is negative. Alright. Okay. It's equal to negative. I need to include that is negative and constant. So minus 9 and it is constant. So our dv dx will also be equal to minus 9. It will have a slope that is constant and negative. Okay. So, but what is the magnitude from? What is the magnitude? Okay. We need to find, we know that slope, the shear is equal to the area under the loading diagram Q dx, which is just basically equal to, of course, it's minus, so just say minus 9 by the length, which is 3, and this gives us a 27. Okay, so it's 27. So what we need to do now is, where we are starting from, we have a 3.75, which is positive, and then we have a minus 27. So they'll need to interact. So we have a minus 27 plus 3.75. So what do you get? Minus 27 plus 3.75. We have a 23 minus 23.25. So what did we say the slope was? Negative and constant. So we'll move from there. This is going to be a straight line. From this point there, it will be a straight line up to somewhere there. Okay. Okay. And this point here, we say this is a 23. It's minus, and this is a 23.25 kilonewtons. Okay. Then once we reach here, we have By, and By is equal to 23, positive. So we have a 23.25 minus 23.25. This gives us a what? A 0. So our shear diagram is going to close, and you expect this behavior. If it doesn't close, then you need to get back and redo your work. You check. Okay, so we have this behavior like that there. Okay, so there we go. So we have positive there, we have negative there. So we are done with our shear force diagram. Great. So what we need to do now is to draw, let me wrap this, to draw the bending moment diagram. Okay, we need to draw the bending moment diagram. So for us to do that, we are going to use the shear force diagram. So let's start from A to D. A to D, our shear is equal to, is positive and constant, is equal to 15.75, and it is constant. And therefore, the slope of our moment is also going to be positive 15.75, and is also going to be constant. And this magnitude, again, we know that is just the area under the shear force diagram, and that one is just rectangular, so it is just 15 by 75 times the length, which is just the 1.5. This gives us 15 by 75 times 1.5. This gives us 23. Where did this line come from? Okay. All right. This gives us a 23.625, right? So 15 by 75 by 1.5 is a 23.625. Great. Okay, so we have all the information. So we look at the boundary again. Boundary conditions are very vital because they will affect where the moment starts from. In our case, we don't have any couple applied at A, and we know that a hinge does not resist any moment. So moment there is going to be equal to 0. So we are starting from 0. So we said the moment the slope is positive, okay, and constant, and the magnitude is 23, the maximum. All right. So we are moving from A to D. Okay, great. So let's move. So positive is going up, right? Let's assume we take it like that, up to there. Great. So this point, let's say this is our 23. This is our 23.625 kilonewtons meter. Okay, let me move it a little bit behind. Let me move it somewhere there. Great. Okay, so there we go. And then, so we found one part, that's at D. So from D to E, what is our shear? From D to E, our shear is equal to a 3.75. It is positive. Let me indicate the sign. It is positive, and it is 3.75, and is also constant. So what does this mean? The slope of our moment dm dx is also going to be positive, okay, and it's going to be constant as well. And what's the magnitude? Again, we are just taking the area under the shear diagram, which is just v dx, and that's rectangular. It's just a 3.75 times the length, which is 1.5. Therefore, this gives us 3.75 by 1.5. What do we get? We get a 5.625. Is that so? 3.75 by 1.5. Yes, 5.625. Great. but you always need to mind where you are starting from. Okay. So we are starting from 23.25. Again, these need to add up algebraically depending on the sign. Both are positive. So to move from D to E, we need to add 23.625 plus 5.625. What does this give us? Let's add 23.625 plus 5.625. So this gives us a 29.25. Let me add again. A 23.625 plus plus 5.625, 29.25. So it has a slope of what? 3.75, and it is positive and constant. So we are just going to move from there to E. Okay, E up to somewhere there. That's our E. Great. So let's say that is our point, and we say this is a 29.25 kilonewton meter. Let's check what happens. Let me wrap this so that we continue from where we are. So we have this part here. Okay, this triangular. I've seen this triangular here. We don't know where it crosses the we can call it the x-axis. So we need to find this length. We need to find this length here. This length here. Okay. So let's just do the basic math here. We find this length. Okay, let's call this x. Right? Because we need that for a triangle. So then what do we do? So what we are going to do, we can redraw this. We can redraw this like so, and then just use similarities of triangles. Okay, so we can say 23.25 plus this top. So we are just using similarities of triangles. Okay, this length 23.25 plus 3.75 divided by this length, which is 3. Which is 3. 1.5 plus 1.5, which is 3, is equal to x. Not x, is equal to 3.75. Okay, this height here divided by x, right? Have I done everything correctly? Yeah. So like that, then we can find x. So 23.25 plus 3.75 okay, then divided by, which is a 27, divided by 3. So this gives us 9. 9 is equal to 3.75 divided by x. Then x, therefore, is just going to be equal to 3.75 divided by answer, which is a 0.4167, right? Have I done this correctly? Yeah. Okay. So this is about it. We have found that length. We needed that length for us to be able to work out the problem. Okay. So this length, therefore, is equal to, this length is equal to x is equal to 0.416 0.4167. Great. So let me wrap this. Right. So we know that at this point where uh, the shear force diagram crosses this zero axis is a point where we're going to find the maximum moment. Right, let's continue. So we have shear, which is decreasing, okay, and this slope is negative, and so it is decreasing, okay, linearly, okay, so it is decreasing linearly from 3.75 to 0. Therefore, we expect our moment, the slope of our moment, dm dx, to also be decreasing. Okay, all right, it's going to be decreasing. Okay, so you can also say, okay, so the slope is going to be decreasing. So let's find the magnitude of our moment, which is just going to be equal to the area under the shear diagram, and this is equal to half times 0.4167617 by 3.75. This gives us 0.5 times 0.4167 times 3.75. This gives us a 0.78, which is a positive, right? Okay, so which of the two slopes here you also draw for you, which is decreasing? This one here, this one here, or this one here? Which one is a slope that is decreasing between 1 and 2? Alright, maybe let me redraw properly the other one. Something like this. Okay, which of the two slopes is going to be decreasing? Mind you, the shear is linear. Okay, so it's a polynomial of degree 1. So expect the moment to be a polynomial of degree 2, which is quadratic, and that's the reason why I'm drawing these curves like this. So between 2 and 1, which of the two slopes or two curves has a decreasing slope? Between 1 and 2. Of course, you already know, right? It is going to be 1. Okay. So we are going to go with 1. Let me just rub out this. So we expect the slope here to be decreasing from this point. We are going to move quadratic. Since the space is too small, it is just going to look like a straight line, something like this. Okay. Something like that, quadratic up to there. All right. So what is the value there? The value there is we calculated the area under this small triangle, which gave us a 0.7813, but we need to mind where we're coming from. We are coming from a 29.25, and both are positive. So these are going to sum up, so it will be 29.25 plus 0.7813. This is going to be equal to 0.7813 plus 29.25. So this gives us a 30.03. Okay, 0313 if you want to. So therefore this value here, which is our maximum moment, is a 30. Okay, even when we have these numbers, these are just coming from rounding off. Okay, kilonewton meters. All right, so we found that the maximum moment. So let's go to the other remaining part. This length here we just subtract from that other length we found, so it is 3 minus 0.4167, 3 minus 0.4167, which gives us a 2.5 2.5833. Okay, 2.5833. All right, so let's look at shear there. Shear from 0 onwards is now increasing in the negative direction. So it is increasing in the negative direction, okay, and the increase is constant, okay. I mean not constant, it's increasing linearly, okay. Of course, yes, it's increasing linearly, okay. It's increasing linearly, and the equation that governs this increase is a polynomial of degree 1, okay, which is just a ym x plus c. Remember this equation. And if this is the case, you expect moment to be a polynomial of degree 2. So slope is increasing in the negative direction, therefore the slope also is going to be increasing in the increasing in the negative direction. Negative in the negative direction. Okay, is that fine? Great. So let's find this magnitude. This is just the area under the shear diagram, and that's just a triangle, so it is just half by the length, which is just a 2.5833 times 2325, and therefore moment is equal to, let's find what moment is. Moment is equal to, so we have 0.5 times 2.5833 times 23.25. So once we multiply that, then we'll find that it is going to be equal to 30.0309. Okay. All right, and this is negative. All right, this is negative. This is negative. So even this moment will be a negative value. So from where we are starting from, we have a 30.013. So they will interact with this one. So we'll have a 30.0313 minus 30.0309. What do we have? A 30 point, of course, we just have a 0, right? That's just 0 minus 30.0309. Okay, this is practically just a 0, okay? 0.0004. This is just a 0, right? Okay, so which is just equal to a 0. So like we said, the slope is going to be increasing in the negative direction. So we expect the slope. We expect the slope. We expect the slope to be quadratic. But let me just ask you. So we say the slope will be increasing in the negative direction. Which of the two curves can we use? This one, which I'm going to call 1, and then this one. Which of the two slopes? Let me draw them properly. This one, let's call this one, and also this one. Which of the two slopes, 1 and 2, will have an increasing negative slope? Which of the two curves will have an increasing negative slope between 1 and 2? Which one? Of course, it is 2, not 1. Okay, it is 2. Great. It is 2. So let's go for 2. So from there, we expect something like that, quadratic in nature. Okay, quadratic in nature or not. Okay, something like that. Okay, quadratic in nature. All right. So this is our bending moment diagram. This is our bending moment diagram, and this is really about it. This is about it, and I hope the video was helpful. Let's check what we have at C. At C, C is somewhere between 0 and 23. What was our shear? Between 0 and minus 23, of course, our shear is minus 9.7. 9.7. You can check it out. And then what's moment? Moment is between 30 and 0. What did we find? 24. Yeah, I think this is about it. We have done the calculations, drawn the bending moment diagram and the shear force diagram, and I hope the video was helpful. If it was, give me a thumbs up, like my video, continue subscribing and liking my channel. Bye bye, and see you in my next screencast.